This is the third lecture in Chapter 18 about electrochemistry, and this lecture will focus on the relationship between the cell voltage, free energy, and equilibrium constant. There are equations, of course, to allow you to convert from one to the other, so let's make sure you understand those relationships. All right, so here is a diagram that kind of helps you visualize it. If we're talking about a spontaneous reaction, one that occurs without outside intervention, of course, hopefully you remember from Chapter 17 that free energy is negative or less than 1 for a spontaneous reaction. And from this chapter, we have learned that cell voltage for a spontaneous reaction is positive. And of course, if they are spontaneous reactions, that means that they favor products, and that means, therefore, that K, the equilibrium constant, is greater than 1. And so here are the three formula that link them, allow you to convert from free energy to equilibrium constant, allow you to convert from free energy to cell potential, and then, of course, cell potential to equilibrium constant. I will provide you with these formula on your test. So here's a little summary table, too. If you're the type that likes to memorize, that you might find that useful. I'm going to talk about each one of those equations just briefly. So I want you to see that it makes sense. We know that if we have a spontaneous reaction, the free energy will be negative. And so, of course, what does that mean? That means that for a spontaneous cell, of course, E will be positive, okay, because the two negatives cancel. All right, so just to make sure you understand what these variables are in the formula, and of course, hopefully you've gotten familiar with, is the number of electrons that are transferred in the balanced reaction. You don't necessarily know that until you balance the reaction, though. F is a constant, which of course I will give you also. It's called the Faraday constant. And it's how much energy there is per mole of electrons. The coulombs provided per mole of electrons. And of course, E is a cell potential. So let's look at an instance where you would use the formula delta G equals minus NF Ecell. So this might be a typical example. You're given a reaction, asked to calculate delta G, and all you're given is electrochemical cell voltages. So the first thing you need to do is find the overall cell voltage when you combine the two half cells, and then you can use the formula to convert from one to the other. So this is a little bit different here. I'm not as concerned that you were able to do this part. If you look at this part and it confuses you, don't worry too much about it. But basically, you remember from Hess's law and other things we've done similar, that you can add or subtract chemical equations just like you can math equations. And so if we are trying to get to this reaction shown on top and we're given these two other reactions, if there's a way to add them together to give us this, then you can do so. And you see here, if you simply add these two together, I'm adding all the reactants together, and all the products together. Then I'm going to cross out what's exactly the same. Everything has to be the same. Charge, everything. And so what I end up with then is the reaction that we have on the top. Let me cross out my electrons also. Okay. And so because I added the chemical reactions together to get the reaction I'm interested in, I also add their cell voltages, half cell voltages together. And So let's see, 0.80, 0.22, and so adding those, you get minus 0.58 voltages. Okay, so what I want you to see out of this, though, is that once you find the cell voltage, you can use that, and all you have to do is plug and chug into the reaction to find delta G, the free energy. You do have to pay attention to how many electrons were transferred in the reaction. Okay, there is one. Be careful of this because let's say that one of these reactions had 2 electrons transferred and the other had 1. Before you can decide what N is for the entire cell, you need to balance the 2 half reactions. So if you balanced it and then found out the N was 2, you would have to adjust for that and plug in 2 here. We didn't have to do this in this equation. Only 1 electron was transferred. F, Faraday's constant, is always the same. I will give that to you on a test. And we just found the voltage was minus 0.58 volts. Watch your signs, okay? Now, what you should think, don't use your common sense. I mean, do use your common sense, that this is a non-spontaneous reaction, okay? So when you calculated cell voltage, you got a negative value. That means non-spontaneous cell. So what mathematical value do you expect free energy, G, to have? You would expect it to have a positive if it was non-spontaneous. So make sure when you do the calculations, that'll help you decide whether or not you have made a silly error with math signs. All right, let's talk for a minute about the relationship of cell voltage to equilibrium constant. If we have a spontaneous reaction, we know that cell voltage is positive, delta G is negative, and of course K, the equilibrium constant in a spontaneous reaction, has a value greater than 1, which simply means that products are favored, which is what you would expect for a spontaneous reaction. It means it goes. And so the equation that you would use to relate cell energy and equilibrium constant is right here. Okay. I want to point out a couple things because you'll see different versions of this formula, including in your lab. These are really the same formula. What has happened is at standard temperature, which is room temperature, which is agreed on as 25 degrees Celsius, which is the same thing as 298 Kelvin. Okay, at standard temperature, they just filled in all of the values for the constants for you. R is the gas constant, which is 8.314 joules per mole times Kelvin. Okay, so they just filled in all these constants for you. And so this is a much more simple version of the equation to find equilibrium constant. Here's a straightforward example for you. Find the equilibrium constant for the following reaction. And this is an easy reaction. They simply gave you the cell potential. So if you think you can go ahead and do that, then pause the video and plug it into the equation. If not, you can watch me work through it on the next slide. All right, so in this case, you just need to know what formula to use. You're trying to find equilibrium constant. The only thing you really need to do on your own here is figure out what N is, how many electrons were transferred. You can do that by simply looking at it, like this one's easy. You're going from iron, which is neutral, oxidation number 0, to iron, which is +2, that is 2 electrons transferred, okay? Now, what I want you to be careful of, what if there's a coefficient of 2 in front of the iron, okay? Be careful then, because the total electrons transferred would then be 4, okay? Because in the balanced reaction, if it showed a 2, it means that each of the 2 ions would transfer 2 electrons for a total of 4. So just pay attention to your coefficients also. And this is another reason why you need to work out sample problems, which are posted in the content folder of D2L, because things like that may not occur to you until you start working problems. All right, so now when you work that problem out, you find that the equilibrium constant is quite large. That is what you would expect for a spontaneous reaction. You would expect K to be larger than 1, and this certainly is. Some of you may be a little bit fuzzy on how to mathematically simplify this equation, so let me just take a minute and show you that. I think most of you can simplify the numbers. You may be a little bit stuck on the log. So you would multiply both sides by 2, and that would give you 0.62 volts equals 0.0591 log of K, EQ. And then you would divide both sides by 0.0591. And I don't have my calculator with me, so I'm going to just keep showing it as a fraction. And that would equal log of K. Now, to get rid of log base 10, log, you raise both sides as an exponent to 10. So it would be 10 raised to the fraction, which you would have figured out ahead of time. Okay. And then when you raise log of something as an exponent, the log goes away. And so that is all you have. So 10 raised to whatever this ratio is equals your equilibrium constant, which should be this value. So I would test yourself, make sure you know how to use your calculator right, etc. All right, so the Nernst equation, which most of you hopefully are working on your last lab report, which involves use of the Nernst equation, and that is for calculating cell potentials that are not under standard conditions. What are standard conditions? Room temperature, 25 degrees Celsius, which is 298 Kelvin, and an understanding that the concentrations of the materials in the cell are 1 molar. Well, even if you start a battery or galvanic cell at concentrations of 1 molar, within a very short period of time, these concentrations are not going to be 1 molar anymore, and you're not going to have a standard cell. And so the Nernst equation honestly is used more often than your standard equation. And so what you need to do, let me just point out how you get these materials. Ecell with the little temperature degree type sign, it's called E0, is standard cell potential, which you look up in the standard reduction tables, and or in the lab. In the case of the lab, we measured E standard cell, and you're going to use your measured value. But for our purposes in the lecture, we will look this value up. And let's use this simplified version. Okay, so really all you need to do now is find the number of electrons transferred. And then what is Q? Same thing as K, except at non-equilibrium conditions. So Q is the concentration of the products divided by the concentration of the reactants. Okay, raised to whatever exponent. If they have a coefficient in the balanced reaction, don't forget the exponent. I want to divert for a minute and show you the relationship between this full version of the Nernst equation and the version of the Nernst equation that we looked at on a previous slide in this lecture. And that was to show the relationship between Ecell and the equilibrium constant. What I'm writing at the bottom here is the relationship or the equation that shows the relationship between cell voltage and equilibrium constant. And I want you to realize that this equation is essentially a form of the Nernst equation. So remember that if we use the full form of the Nernst equation, we're implying that we have a working battery, one that's not at equilibrium. If you have a reaction in equilibrium, that means the battery is used up. Okay, there's no further driving force, no chemical reaction to occur when you're at equilibrium. It's already at the lowest energy point. But look at the full version of the Nernst equation in the middle of the page here. And what happens if we're at equilibrium? If we're at equilibrium, E cell goes to 0, Okay? No voltage, no driving force. And at equilibrium, what happens to Q? Q is now called K, equilibrium constant. And so making those two changes gives you the equation we used on the last slide that related Ecell to equilibrium constant. Now, although standard cell voltages, which are in the reduction tables we use to do our calculations, are very handy, but they don't really make the best batteries. It's to our advantage to not use standard molar concentrations because we can make a battery last longer and also give us higher voltage. So let's look at a voltaic cell or battery on the left here under standard conditions where both concentrations of the electrolyte solutions are 1 molar. We get a voltage of 1.10 volt. Okay, that's standard right off the table, and that's what you'd get if you made that cell. Now, if instead of using 1 molar solutions of the electrolytes, we used a much higher solution of the copper electrolyte and a much lower solution of the zinc electrolyte, why would that be, or what would happen? What would happen is the cell voltage would go up. So you need to be able to understand why that is. And I think to help you do that, let me write out the balanced reaction first. I'm just going to combine the half reactions into one overall balanced reaction. So at the anode, undergoing oxidation is zinc. At the cathode, undergoing reduction is copper ions. And then, of course, what is produced at the anode is zinc cation. Comes off the zinc metal and drops into solution. And what is produced at the cathode is copper metal, and that plates onto the cathode. And so the Q value for this reaction would be the concentration of the zinc cation in the electrolyte solution divided by the concentration of the copper cation. Remember that we leave solid materials out of the equilibrium expressions. They don't affect it. Only the aqueous salts are included in the expression for Q. So now that we have the expression for Q, look at what's happened to the second battery on the right. We've increased the concentration of copper, and we have decreased the concentration of zinc. Okay, so what has happened here? You think of it from Le Chatelier. I think that's the easiest way to do it. If you increase the concentration of the reactants, which way does that push the equilibrium? It pushes it or drives it to the right. And anything that drives an electrochemical reaction to the right is going to increase cell voltage. That's where cell voltage comes from. It comes from the reaction proceeding as written from left to right. And so that explains the higher cell voltage. You can also check it out mathematically if you'd rather. If you change the value of Q by increasing the denominator, plug it into the equation, you can prove to yourself that the resultant cell voltage would go up. So let's go through a standard Nernst equation calculation just to get you familiar with plugging all the values in. And you can see here that you are given concentrations. It's expected in this case that you know that soluble salts, as soon as they dissolve in water, dissociate to give you the cation and the anion. Okay. The nitrate is a spectator. It's not going to end up being important. But as you use the Nernst equation, you are going to need to realize that if they give you the concentration of zinc nitrate, for example, they're really giving you the concentration of the zinc cation. Okay. If you think you can work it out, give it a try, plug it into the Nernst equation, and then compare your answer on the next page. All right. so here is the Nernst equation, and Ecell will either be given to you or you'll have to calculate it. It's 1.10 volts, standard Ecell. The number of electrons transferred is pretty easy in this case. It's clear to see that there are 2 electrons transferred. Zinc loses 2 electrons and copper gains 2 electrons. So N is 2. And Q, okay, is products over reactants. So that is the zinc cation over the copper cation concentrations. And let's see, zinc cation concentration is 0.5 and copper cation concentration is 1.5. So now you just want to make sure that mathematically you can solve this. And what has happened is the voltage has increased versus the standard voltage of 1.10. Not very much, but anytime the voltages increase, that means that the concentration of reactant has increased. And if you look here, that's true. Concentration of the copper ion has gone up above standard conditions to 1.5 molar. And the concentration of the products, instead of being 1 molar, has been decreased to 0.5 molar. Again, from the viewpoint of Le Chatelier, when you increase concentration of a reactant, you drive the reaction to completion more. And for electrochemical cell, it means the voltage goes up. So here's a reaction or a problem that puts it all together for you. It links all 3 values: free energy, equilibrium constant, and cell voltage. And so it gives you the 2 half reactions and it asks you to calculate all of those. In most cases, as in this, you're going to start by calculating the standard cell potential. And so, of course, the first thing you need to do, and you should be able to do this on your own, so really good test for yourself at the end of this, but you want to determine which of these 2 half reactions to flip, because of course, as always, they are both written in terms of reduction. I know that on the last quiz this confused some people, so I'm going to assign oxidation numbers. Some people thought on the last quiz, since manganese dioxide appears to have a neutral charge in this compound and then goes to +2, they were thinking maybe this already represented an oxidation reaction. That is not the case, and I'm just noticing now that I'm leaving out electrons too. All right. So assign oxidation numbers. If there's any question in your mind whether or not something's being oxidized or reduced, assign oxidation numbers to every single atom. I'm going to do that to manganese dioxide. I'm going to give oxygen a -2, which means manganese in this compound has to be +4. So now it's easy to see that the manganese has gone from +4 to +2. How does it do that? By gaining 2 electrons. Okay, so there really should be +2 electrons here on the reactant side. Alrighty, so looking at the standard reduction values, you always want to flip the one that has the lowest value. That's obvious. If one of them has a negative sign and the other doesn't, you're going to flip the one that's negative. So I'm immediately going to flip the potassium reaction and make it be oxidized instead of reduced. And that means that its Ecell value will equal positive 2.92. Okay? Go ahead and see if you can work the rest of this and get K and G, and then I'll show you. You can compare your answer in the next slide. Now, it's likely that you're going to have to balance the half reactions in order to determine how many electrons are transferred. If you're able to do this in your head, that's fine, but I would recommend balancing them to make sure. But you can see here that 2 electrons have been transferred in the manganese reduction half reaction, and only 1 have been transferred in the potassium oxidation. And so before these 2 would be combined, you would have to multiply the oxidation half reaction by 2. So that would give you 2 potassium, makes 2 potassium ions, and then 2 electrons released. Okay? And so that makes it clear then the N, the number of electrons transferred, is 2 for this reaction. You'll need that for the equation. All right, so step 2, just to make sure, is to write a balanced combined reaction and calculate the Ecell. And so here's the balanced reaction, and the electrons on both sides have canceled out. Remember, when you're writing a balanced reaction, that you should end up with electrons on the reactant side and on the product side, and that the number of electrons should be the same on both sides so that they ultimately cancel. You should never see electrons show up in the final balanced combined reaction. And so that gives us the Ecell for the entire cell is 4.15 volts. Now it's just a matter of simply plugging into the formula that we have to find free energy and equilibrium constant. So here is the free energy equation. We have 2 electrons that we've transferred. Don't forget the negative sign. Remember that we found this is a spontaneous reaction, so we expect the mathematical value of G to be negative. Here's Faraday's constant F and the Ecell that we just found. So that means that the delta G, or free energy, is about minus 800 kilojoules. Notice that the units in this case are kilojoules, all right? And that kilojoule value is inherent in the Faraday constant units, so that's kind of important to know. The last thing I want to leave you with in this third lecture is there is something called concentration cells, where you have a voltaic cell, in other words, it's spontaneous, and you know how we have an anode and a cathode, and typically the anode and the cathode are different things, and typically our electrolyte solutions are different electrolytes. You can have an electrolytic cell, a galvanic cell that has the same electrolyte solution and the same anode and cathode. But the caveat here is that electrolyte concentrations must be different. If the concentration of the electrolyte is different in the 2 half cells, there'll be a driving force. This is a little bit counterintuitive, so make a note of this. The electrons in a concentration cell will flow from the electrode in the less concentrated solution to the electrode in the more concentrated solution. So let's say that I have zinc on the left side, zinc electrolyte at a concentration of 0.1 molar. And let's say on the right side I have the zinc electrolyte concentration at 0.5 molar. The electrons would then transfer from the left to the right, less concentrated to more concentrated. Let's try to think logically of why that would be. If the electrons are being dumped into whatever side they're being dumped into, what are they being used for? They're being used for combining with the electrolyte in that half cell and making the neutral metal, which then plates out onto the electrode, okay? What does that do? You're essentially, by pumping electrons in, you're essentially removing electrolyte solution. That makes sense, right? If you're dumping electrons into the more concentrated side, and by removing the electrolyte, you're making it less and less concentrated, and you're equalizing the 2 half cells. So a typical multiple choice might be to show you a diagram of a concentration cell with the concentrations labeled. Your first goal would be to find the half cell that is the least concentrated, lowest concentration, and then know that electrons are going to flow from that half cell to the more concentrated half cell. That means that the least concentrated half cell has the anode, okay? Again, This is only when you're dealing with a concentration cell, and that means only when the two half cells have identical substances in them. The whole rationale I'm going through doesn't apply if the two half cells have different substances in them. Let's say zinc and copper or something. Only when it is the same substance but at different concentrations. That's it for the third lecture. There will be one last lecture on non-spontaneous cells, which are called electrolytic cells or electrolysis.